Okay.
We're going to start talking about DC circuits. Okay, we're going to start talking about DC circuits. So we talked about resistors. So how do you make a resistor? Choose a material. You have length and you have width, right? So here is some material, and you have a length, and you have a cross-sectional area A, and it has resistivity rho. So the resistance is going to be rho times L over A. So if someone says, make me a 10 ohm a 10 ohm resistor, you know how to make it. Choose the material and then appropriately choose how long and how much area it should have. Okay? So you can choose, you can make the resistor. All right. So how does a resistor look like? It looks something like this. But in a circuit, we like to do it like this. This is a resistor. That's the symbol for a resistor. That's a resistor. And we're going to say, here's a circuit, you got a battery. So that's the voltage difference, the potential source. It has some voltage, we call the EMF or the voltage, right? Let's say 9 volts or something. There is a switch, and then you got your resistor, and then the circuit is completed. This is the resistor R. This is called the switch, and then when you close the switch, there will be a current. So let me close the switch, and then ask, what's the current? Or in what direction is the current, first of all? In what direction is the current? It's going to be clockwise. Good. So the current is going to be in the clockwise direction. So you got current this way, it passes through the resistor, and then goes, that's it. So DC circuits, direct current circuits, as opposed to AC circuits, alternating current circuits. DC means the current does not change its direction. It will always, if it starts clockwise, it will just keep going clockwise. It doesn't alternate between clockwise and counterclockwise. Okay, so that's DC. So that's our focus. It's just going to be in the same direction. Yes.
So in this, there's no parallel or circuit or parallel or series with it?
There is, but in a moment.
Okay.
Yeah. Yeah. For now, we have just one resistor. So when we can have more resistors in that case.
Crossover?
Yeah. So we will get to it at some point. So let's apply the loop rule and then ask. Right. The loop rule says the change in potential around a closed loop is 0. And so let's start here and ask, what's the change from here to here? Positive this, right? E or V voltage. Nothing goes on. How about here, from here to here? Yeah, so this is the intuition I want you to have. When you go in the direction of the current, you're going in the direction of the electric field. And so in the direction of the current, direction of the electric field, the potential change is negative. It will be, current flows from a higher potential to a lower potential, so the change is negative. So minus. Minus what? By Ohm's law, we said the potential from here to here is the current through that resistor times the resistance of the resistor, right? Ohm's law said V is equal to IR, right? So it'll be I times I. So it will be the current times the resistance, right? So the current through the resistor times the resistance of the resistor is the potential across that resistor. Okay? I know, it's repetitive, but yeah. So what's the total change?
0.
So yeah, so that means the current I will just be E over R, right? which is obvious, I think, because we already said the potential across the resistor, or the resistor experiences the potential of the battery, right? The entire potential. If the battery is 9 volts, what's the potential difference across the resistor? It will be 9 volts, which is not surprising. But it's good to start with just one resistor at first.
Oh, what does AC means? The alternating circuit?
Alternating means the current changes direction. It could go, like this one is clockwise, right?
Yeah.
And if we continue clockwise, that's DC. AC, you might have a battery. Let's say someone here keeps switching the battery, the plus and the minus. Physically keep flipping the battery. That would be AC.
Oh, AC.
We will not worry about it at the moment. For now, it's DC. Any questions up to this point? Looks good?
But,
Yeah.
so current will always work one way, right?
Yes. Yes. It doesn't change direction. Yeah.
So,
Current works.
this kind of looks like the same figure as when we had a battery and just a capacitor, and
Yeah.
we were like pressing down from here to here, positive V, from there to there,
Yeah.
from there to there. We're basically kind of doing the same thing.
All of current works two way?
For a capacitor, there was no current. It just charged. But let's not. We will combine the resistor and the capacitor together in the same circuit. We will have a current, and then we will see what happens to the current.
Depends on the
Yeah.
plus negative.
So, yeah, that's. There would be similarities, definitely.
What is the about a closed circuit with nothing but a battery then?
It would die very quickly. Yeah. Have you tried to connect the wire to a battery only? What happens to your fingers? You get really hot quickly. Yeah. So let's, in fact, yeah, let's get to that, because there would be energy consumed by the resistor. Okay. So let's go to, so first of all, is this clear how I applied the loop rule? Also, the loop rule, it comes from here. I think I already mentioned it, but remember, all of these, they came from what we already know, the basics, right? We said the definition of the change in potential was what? Minus the integral of d dot dr, right? If it's a closed loop, you start at a point and you end where? At the same point, so you get 0, right? So, but we don't have to think about the integral, though. We just need to remember the rule. Over a closed loop, you get 0. So that's actually makes sense. Okay, so that's that. Next, how much work is the battery doing to complete, to make this circuit like this, to drive the current, right? Because what the battery has to do, it pushes positive charges, they get through the resistor, they come back here, so the battery has to push the positive charge from the minus terminal to the positive terminal, and then it goes again. I gave you the analogy of what? The ski, right? Slide down, that's passing through the resistor from higher potential to lower potential. Now you're at the lowest point, and then you climb yourself or just use an elevator. The elevator is the battery. That's the one that takes the charge up and then repeat. So the question is, how much energy does it cost? Let's say I have a charge dq here. What's the energy to take dq from here to here? Let me write here. du is would be dq times the voltage, right? And the voltage of the battery is the EMF, is the volt V. Is that clear? Yes. You remember that U is QV, right? Yeah. So what if I divide both sides by dt? What's dq dt? I. Just I. And then this one, the voltage. What's du dt? Power. Energy per unit of time. Yes, it is power. Capital P or power. Let's rewrite that equation. So I get this, power is I EMF, right? So we can write it as IV, right? Because V is the voltage across the capacitor. Resistor. IV. Now, just like the capacitor, we had three different forms for energy. We'll have three different ways to write power. Let's first eliminate the voltage. Let's see. The voltage or the EMF is IR, right? IR. What if I replace this V or the EMF by IR? What do I get? I times IR, what do I get?
I squared R.
I squared R, right? Let's put another equal. Now let's replace I by V over R. Right? If I replace I by V over R, what do I get? I get V times V over R is
V squared over R.
V squared over R. So these are different ways to find the power. We'll do an example. Yeah.
So, you said that the power is the amount of work that you did to move the through a very small t distance out?
It's the amount of work needed to take a charge across a voltage V. Let's say this one is maybe 10 volts. So to take a charge across a potential through a potential difference of V, through a potential difference of V,
Oh.
and the amount of energy is dq times that potential difference.
Okay.
You remember, like, just think of the parallel plate capacitor. Just to, so let's say this is plus, this is minus. How much energy does it take to take a positive charge, let's call it little q here, across a potential V? What's the change in potential energy to take the charge from here? That's the change in potential energy to take the charge. So which form do you use? Well, any of them. Any of them is okay. Let's do an example. We'll go to the next. Okay. So let's say I have two resistors. Here is a battery. Let's say it's 10 volts. Let's say I have a resistor here, and then another resistor here. Let's say this one is 10 ohms, and let's say this one is 40. 40. So I have two resistors, right? And let's name them. Here is called R1, and this one is R2. So we know what it's referring to. First question is, let's find the current through the circuit, or through the resistors. So let's say I have a charge, first of all, in what direction will the current go? Clockwise? Yeah, clockwise. So the current goes this way. Will the current passing through R1 be the same as the current passing through R2? Or no, or yes?
Yes. No.
Okay. Why not, or why yes?
Same.
Same, why the same?
Same charge.
Charge?
Same charge. Wait, is Q yeah, same, right?
So let's say I've, if you say it's not the same, right? It means, let's say you have 1 coulomb rate per second passed by, and just half a coulomb comes out per second. Where does the rest of the charge go?
Resistor.
Yeah, it can't just disappear, right? By conservation of charge, whatever passes through this one has to pass through this one. And whenever you look at circuits, think of the analogy with what? You have a wide pipe, and then it becomes narrow, but still, the amount of, if you have 10 gallons per second passing by, you have to have 10 gallons per second coming out of the other side. You can't just have, or cars passing through a tunnel. You can't have 10 cars going in and just 3 only coming out. Where did the rest go? Okay, so by conservation of charge, the current through R1 has to equal to the current through R2. Their current is the same. So the current throughout the circuit, when you just have one branch in this case, one loop, it's the same. The current is. So the current I1 is equal to I2, and it's just I. Okay, we'll just call all of them I. Let's apply the loop rule. Let's apply the loop rule. Start here, and then go here. What's the change from here to here?
10 volts.
It'll be 10 volts. Yeah. How about the change from here to here? Is it going to be a plus change or a minus change? Minus, because current flows from higher potential to lower potential. So minus. Minus what?
Minus
V1.
IR.
V1. Okay, let me call it V1, the potential difference across R1. Let's call it V1. And then, for now. And then minus V2. And then back to 0. So we get 10 is equal to V1 plus V2, right? But Ohm's law says what? The potential difference across a resistor is equal to the current through the resistor times the resistance of that resistor. So I1 times R1, right? I1 times R1. So I have here I1 times R1. But I1 is I, so I'll just call it I. And then for number 2, it would be what? I2 times R2, so it's just I times R2. So you get 10 is equal to I times R1 plus R2. Okay. And so I will equal to 10 divided by R1 plus R2. So that's 10 plus 40, right? R1 is 10, R2 is 40. So 10 over 50, which is 0.2. So 0.2 amperes. That's the current. Okay, good. Let's find the power consumed by the first resistor. How do I find the power through the first resistor? Let's call it P1. I squared R1. Good. Yeah, I can just use the current. It's I squared R. I wouldn't use V, because I need to know V1, and then to get V1 I need to do I1 times R1. Why do that when I can just use I squared R? I already have the current. I squared times R1. It's I1 squared R1, but I is I1. So I get 0.2 squared times 10, which is what?
4.
No.
0.4.
0.4? I think it's 0.4. 0.4
What?
joules per second, right? Watts.
What?
The power on the second resistor is what?
I squared.
I squared R2. So I get 0.2 to the power 2 times 40. So it'll be what, 1.6? So now, who is provided this power that's going through this resistance? The battery. Okay, so what's the power provided by the battery?
VI.
Huh? of the battery, which is like this, EMF or V. So I get 0.2, yeah, 0.2 times 10, which is 2 joules per second, right? Is the total 2?
Yes.
Yeah. Okay. So that was that example. And you can see already those resistors back to back like that. It's called resistors in what kind of combination? Series. Those are series. And when they're in series, you notice their resistance just adds. Right? Resistors in series, their resistance simply adds. Okay. So when they're in series, their resistance is simply adds. But we haven't talked about that yet, just to observe that. Let's do one more example, and here is this example. A battery will have some internal resistance to it. The battery will have its own internal resistance, a little bit. Okay. So, and it looks like this. Looks like this. Here is the battery, and it has its own little internal resistance, little R. And this is the voltage of the battery. When you look at the battery, you're looking just on the outside. This is the outside, this is the outside. Okay. And I'm going to connect it to some resistor, capital I. So let's first find the current in this circuit. So you can treat it just like we had earlier, a battery, a little resistor, and a bigger resistor, capital I. So what's the current? So let's do part A. Find I in terms of obviously the EMF of the battery, the internal resistance, and capital R, right? Those are the givens. So we need to find the current in terms of those. So I is current, right? Not V. So how can we find the current? What's the difference between that one and this one? It's exactly the same. Yeah, so the current would just be the voltage of the battery divided by the sum of the two resistances. Okay. So current would just be B. Find the PR, the power consumed by the resistor capital R. What would be the power consumed by that resistor capital R? Okay, so you say PR would be I squared times R. Yeah. The current through the resistor squared times the resistance of that resistor. So do that. You will get E squared over R plus little r squared times capital R. That's the power, right? C. So C asks the following. You got a battery with its own internal resistance, so the voltage of the battery doesn't change. This one doesn't change. Suppose you change this resistance. You vary. You start with maybe no ohms at all, zero resistance, 1 ohm, 2 ohms, 3 ohms, 5 ohms, and you ask, what should capital R be so that the power consumed is maximum? Okay? So, for example, let's say capital R is 0. What would the power consumed be? 0 times something 0, right? And if capital R is very, very large, approaches infinity, what does this approach?
Zero.
This the numerator is approaching infinity, but denominator approaches infinity squared. So it will approach 0 again. So somewhere in the middle between 0 and infinity, the power is maximum. You get some maximum. Okay. And so the question is, what should capital R be so that the power consumed by this capital R is maximum? What do you do? Yeah, we should say take a derivative. And that derivative would be the power as a function of R. So is the question clear for C? What should capital R be in order for the power to be maximized? So you need to do this. So let's do it. I have to take this derivative, and let's start with this. It's a product, so derivative of this is 1. And minus derivative of this, we have
Isn't it plus?
it's to the minus 2. So minus 2 comes down. Right? I just took the derivative. So just slowly take the derivative. And then you do that. Equals to 0. And move this to the other side so you get. So this cancels. This whole thing cancels this. So you get on the left side just the number 1. On the right side you have 2r over r plus little r. Cross multiply, you get r plus little r is equal to r. That means capital R is equal to little r. That's when the maximum happens. And if you plot the power, this function, with respect to r, here's r, here's the power. I think it looks something like this. When capital R is equal to little r, the power consumed by capital R will be maximum. Right.
Why would you want your power consumed by the resistance?
Just for mathematical reasons.
Okay.
Just as practice. Not for any practice.
Also, you said that R and R are in series.
Yeah.
Jadi untuk ada power harus ada.
Are they not on the same branch? The current that passes through little r has to pass through capital R. So the next would be we're going to do parallel and series. So let me just draw it because I don't have much time. So I'm going to ask you, what do you think? Or let's do it this way. What kind of connection is this?
Series.
That's series, right? Yeah. Is that clear? You don't have to draw them one next to the other on a straight line. As long as they're on the same branch, they're in series. Is that okay?
So for the power to be exist, you have to have resistance.
Yeah. If you have no resistance, then there is no current going through a resistor, so the power would be 0. Yeah.
What would the power be so if I had resistor and capacitation for the battery?
You're saying if you have a perfect conductor and a perfect battery with no internal resistance, right? the current will run for exactly basically 0 time. Yeah, it will die immediately. Yeah. Yeah, that's why it heats. The wire is a conductor, but there is a little bit of resistance when you, if you just connect the battery like that. Don't do it.
The
That's
wire
a-
just
Yeah,
Not that I've
the
done
skin
it,
of the,
or,
yeah,
you
the
know.
plastic will melt, yeah, it does.
So, you said that like the current at the circuit is equal to it, like the purchase mode, right? Then what exactly is the resistance? What is the resistor resistor, right?
Well, because if the resistance gets larger, the current will be smaller, the overall current. Right.
The current time period of this circuit.
Yeah, right. So for example, here, if, right, it's the potential difference divided by the resistance, right? The sum of the, so if the resistances are huge, this current would not be 0.2, it would be something else, right?
Yeah, but you said that on a closed circuit,
Yeah.
the current at any point in that circuit is equal to another point.
Yeah, it would still be equal, but it would be a smaller number.
The more
Yeah.
resistors you have.
Yeah.
Oh, because they're adding this.
So we will discuss this next time. We continue to parallel and series.
No,